Hello again, everyone, in your channel, um, Basic Engineering. And today we are going to start analyzing real structures. And the first one we are going to use or analyze is the truss. Trusses are very simple structures. And the reason they are simple, they are made exclusively of two force members. Remember, we talked about two force members. I told you if I have a member that is only connected at its two ends, so if it's connected, say, at two ends and another point in the middle, then it's no longer a two force member. But it's only connected at its two ends, and if loaded, it's only loaded at its two ends. Why does that make it like special? It's because if that's the case, then the force in this member would follow the line joining the two ends of the member. Again, in trusses, most of the members are linear. So in that case, if it's a two force member, then the force is along the axis of the member. It's not inclined. I don't have an X and a Y components. No, it's only one force, okay? The only thing I need to know its magnitude and whether it's compression or tension. But it's much easier than, say, frames or machines where you may have at least one non-two force members. Many non-two force members exist. So trusses, we can define them as structures made exclusively of two force members. So I may have a truss. Usually you have a lot of bridges, roofs of, say, manufacturing plants or like big depots that where we cover them with trusses. Okay, so the truss would look something like that. You just draw one, not to scale, not anything, just and maybe I will have that several bays. So maybe I will have a member like that. Let's do a quick one. Very simple truss. Um, okay, so I have a truss like that. A, B, C, D, E. And maybe there are some forces. So there is a force here. Let's say F1. I have a force in F2, a third one here, F3. And in order for this truss to be statically determinate, I will have, say, a pin on one side and a roller on the other. Now, let's think about the number of unknowns that we have and the number of equations. In order for that to be statically determinate, I need to have as many unknowns as I have equations. If I have less unknowns than equations, then it would be unstable structure. It would fall. If we have more unknowns than we have equations, it will be statically indeterminate, meaning if you use statics alone, you won't be able to determine the magnitude of all the unknowns. So what are the unknowns? Well, the unknowns, remember we did a pin and a roller so that we have three unknowns, always three, right? Because you have three equations of equilibrium, right? So I have unknowns are three, which are the reactions at the supports, plus the force in each member. I don't care about whether it's tension or compression for the time being, but how many members do we have? 1, 2, 3, 4, 5, 6, 7. Okay? We are going to refer to them as M, number of members. Notice 7 plus 3 is 10. And how many equations do I have? Remember, we just said that the truss is made exclusively of two force members, meaning this force is along line AB, the force here is along line BE, and the force here is along line BC, and the force F3. All of them intersect at B. What does that make B? Yes, a particle. These five joints are particles. Particles in 2D. So how many equations of equilibrium can we write for each of them? Each one of them. Some of the forces in the x equals 0, some of the forces in the y equals 0. So if the number of unknowns or the number of joints is j, so m for member, j for joints, I have two j equations, some of the forces in the x and some of the forces in the y. And that is how I check to see if my truss is statically determinate. If the number of equations is more, so if I have that, I would say unstable. And if I have that, meaning m plus 3 is greater than the number of equations, meaning you don't have enough equations to find everything, it's statically indeterminate. So these joints are pins. And these pins are very smooth. Why do we say smooth? Because if they were not smooth, of course, there is no such thing as a purely smooth connection, right? There will always be friction. But if the friction is so small as compared to the magnitude of the forces, either outside forces or inside forces, the forces in the members, then we can ignore them. Otherwise, if there is friction, notice the friction resists the rotation, moments. Oops, there would be moment at B, moment at C, moment at E. Oh my God, moment at A and D. And in that case, we say, oh, I can't even touch it. So they are structure made exclusively of two force members connected by frictionless joints. That's the key. Okay. Now, what we are going to do is usually we are not going to start writing 10 equations in 10 unknowns. It doesn't make sense. If in the very rare cases that I have a pin that has only two unknowns, I can start there. For example, here I have 1, 2, 3 unknowns. The force in these three members. Here I have 3 unknowns. The F1, F2, F3 are known. Here I have 4 unknowns, 2 members and 2 reaction components, because that's a pin, has an X and a Y, and I don't know either. Here I have 4, 1, 2, 3, 4. Here I have 3. The Y, because this doesn't have an X, the Y for the roller and the member forces. So, oh my God, I'm stuck. I cannot start. Or can I? Yes. Here is the key. It's always safe to start by considering the whole truss. The whole truss is a rigid body. Yes, each pin. So that's a rigid body in which we have inserted 5 particles. So I can either look at it as specific particles, or I can look at it as a whole rigid body. Before we continue, we have to say we have 2 ways of analyzing trusses analysis. I have 2 ways. The first method that we are going to use today is called the method of joints. And the next one, probably I will take that tomorrow, is another method called the method of sections. So what's the difference? The way I look at it, there is no difference. The only difference is that the method of section, I cut the truss and separate it into two pieces. And by doing that, I can analyze each piece separately. Okay, why would I do that? Well, we will see some examples when it makes more sense. Okay. The method of joints, I don't see the only difference I see. I say the method of joints is that I will go to each joint and cut it by a section. So I would make a section like that, and now I can separate A from the rest of the truss. Or I can take a section like that and separate this joint from the rest. Hence, we call it the method of joints. I separate joints. I separate joints like that. Don't worry, it's so easy. I know I may have made it complicated for you, but I just want you to understand that we have two methods of analysis. Today we are going to look at the method of joints, but as I said, I'm not going to write 10 equations of 10 unknowns. Unless I have a computer, it's going to take me forever to solve a 10 by 10 or a 10 by 11 matrix to make it in reduced row echelon form, right? Doesn't make sense. So what makes sense? I will tell you. As I already gave you a hint, I say, I'm going to look at this whole truss as a rigid body. And as a rigid body, I have three equations of equilibrium. By the way, please be careful. These three equations of equilibrium, which is sum of the forces in the x equals zero, sum of the forces in the y equals zero, and sum of the moments about any point equals zero, they are not extra equations. If I use them, then I only have 2j minus 3 equations of equilibrium that I can use. I'm not creating new equations. I'm using, instead of saying I'm going to use two here, two here, two here, two here, and two there. No, I'm going to use three for the whole truss. Why is that? Because now if I take the moment, say about point A, take the moment that F1 produces, F2 produces, and F1 produces, and dy produced, the only unknown is dy, so I can find dy. Sum of the forces in the x equals 0, I get ax. Sum of the forces in the y, now I know dy equals 0, I get ay. So now the three reactions would be known. Now, if I cut this section, this joint, I only have two unknowns. I can solve with sum of the forces in the x and y. Here, I have two unknowns. Once I solve these, I can move here, and now instead of having three unknowns, I only have two, and so on. And so I move one joint at a time, and I will never have more than two equations in two unknowns to solve simultaneously. Later, I'm going to talk about some simplification, which is called the zero force members. We'll talk about that later, but for now, I hope you understood what I said. A common mistake, let me reiterate to tell you something extremely important that would make your life much easier. Remember, we have internal forces here that we don't see. They don't exist. Why? What do you mean they don't exist? Well, they exist, but let's assume if this member, for example, let's assume that okay, this member is under compression. Okay, let's assume it's under compression. I'm going to draw the forces in it like that, meaning this side is compressing this joint and this side is compressing joint C. I've seen students don't know how to take moment about A because they say there are two forces here, two forces there, and every member has two forces. So how, and I don't know their magnitude, so how I take a moment here? I say, no, these internal forces are hidden, they are transparent, they are like ghosts. You don't see them unless you separate the unless you cut the member. When you cut the member, you are exposing two equal and opposite forces, either going into each other or going away from each other. But as long as the member is intact, like the whole truss, They cancel their they cancel each other. They have the same line of action, opposite sense, and equal magnitude. So if you want to take the moment, be my guest, but it doesn't make any sense. I'm going to say the moment produced by this force is clockwise, and the moment produced by that force is counterclockwise. They have the same magnitude, they are the same distance away from point A, so they produce zero moment about point A. So all these internal forces are hidden. I assume they don't exist. I don't care. I only see the external forces. All the internal forces come in pairs. They are equal, they are opposite, they are collinear, meaning they cancel the effect of each other. Let's take an example and see how we find the force in these members and the forces at the support. Oops, reactions at the support. Think I have two. Okay, I had two examples. So this is the first example. I have a truss that has a roller on the left, a pin on the right, 1, 2, 3, 4 times 2. I have 8 equations of equilibrium. How many unknowns? 3 component of the reaction, 1, 2, 3, 4, 5 members. Notice AC is not a member because if it were, it's connected in the middle, so it's no longer a two-force member. But AB is a member, BC is a member. I have 5 members, 3 component reactions for a total of 8. 1, 2, 3, 4 times 2 equations equals 8. So it's statically determinate. Now, of course, I have to redraw it for the free body diagram. So I'm going to do that. Of course, I'm not going to measure anything. I'm going to just draw the free body diagram as something that looks like that. It's not to scale at all, just because we don't have time. Don't want to waste your time. There is a member here. There is a force at D, 450 pounds. I have to show the dimensions because without them, nobody can solve that. And the height is also 4. Notice I'm going to, for the total truss, I have to show the reactions. This is a roller, so I have A sub Y. This is a pin, so I have C sub Y and C sub X. Notice I assume everything is positive, and then if I get a negative sign, it means it's in the opposite direction. I also, since I'm going to use summation of the forces in the X and the Y equals 0, I have to show the X and the Y. That's a complete free body diagram. There is nothing else except to say that this is 4 feet that is missing, right? Notice I have 3 unknowns here, 3 unknowns there, 3 unknowns here, and 4 unknowns there. So I have to start with the overall equilibrium. Okay, I'm going to say summation of the moment, say about point A equals 0. I only have 3 forces. Cx passes through A, so it doesn't produce moment. I have the 450 going counterclockwise, so that's a positive moment. And the vertical distance is 4, right? This is a positive moment of magnitude 450 times 4, or 1800. The Cy is also going counterclockwise, so plus 8 Cy equals 0. First, I can simplify by 4, in fact, by 8. And this is 4, and I divide that by 2. So I get Cy equals negative 225 pounds equals 225 pounds down. You don't have to redraw it because you already said here is the correct direction. But then when you use it in an equation, you don't use it as going down, not up. But I don't have to cross out and change that. I already said it's negative. So I'm saying to the grader or whoever wanted the analysis that CY is drawn incorrectly. It's negative, meaning it's going down. Then I can say summation of the force in the x direction equals 0. I only have Cx going to the right, so it's positive, and 450 going to the left, so it's negative, which means Cx equals 450 pound positive, meaning it's going to the right. And finally, I say sum of the forces in the y equals 0. I have Ay going up, and CY, notice, going down. So minus 225 pound equals 0. So AY equals 225 pound going up, meaning I drew it correctly. And here, I want you to see something interesting. Again, it's not hard, but I want you always to look at what we've done. Of course, Cx is 450 because these are the only horizontal forces. They have to cancel each other. But did they cancel each other? No, they are a couple. 450 to the left, 450 to the right, a magnitude of 4 between them. So they produce a positive. So I can take them out and draw a counterclockwise moment of magnitude 1800. Huh, so is the stress going to return counter? No, I have AY going up, CY going down, a distance of 8, and 8 times 225 is 1800 going clockwise. So really, this truss is subject to two equal and opposite couples of magnitude 1800 each one, and they cancel each other, and that's why the truss is in equilibrium. I mentioned earlier we have something called zero force members. Where is a zero force member? It's member BD. Why is BD a zero force member? Because if you have a joint that has three like three members connected to that, like here there are three, here there is three. If there are three forces connected to or three members connected to a joint, two of them are collinear, then the third one is a zero force member. We draw a zero like that. We'll explain it in more detail later, but that is a zero force member. I don't have to worry about it. Now that we know AY, CX, and CY, I can start at A or at C. It doesn't matter because I already know one of the three unknowns or two of the four unknowns. So let's say we are going to draw the free body diagram of joint A. What do we have at A? At A, since we assume everything is tension, as if we don't know, so I'm going to say force, I'm going to call it AD, which is the name of the member, instead of say F sub AD, and I have a lot of Fs and a lot of subscript. I'm going to say AD, AB, and we found that AY is 225 going up. That's a particle, by the way. And here is my X, here is my Y. Okay? And that's not a complete free body diagram. Why? Because I don't know this angle. Should I know this angle? Of course. Do you see that this is a right triangle? The base is 4, the height is 4, so this angle is 45 degrees. So now I can write my two equations of equilibrium. Should I start with X or Y? So I hear someone it says it doesn't matter. We usually start with X. Now, why should I start with Y? Because if I start with X, AB is along the X and AD has an X component, so I will end up with one equation and two unknowns. Why? But if I do the Y, AB is horizontal, so it doesn't have a Y component. So it makes more sense to say summation of the force in the Y direction equals 0. AD sine 45 is going up. 225 is also going up equals 0. So AD equals negative 225 over sine 45. Notice, I assume everything is going away from the pin. Away from the pin means tension. Meaning, if I draw two arrows, it's not correct, but I'm saying there is two internal forces like that. These are tension. Why? Because this is what the member is doing to the joint. Notice I'm analyzing a joint. So I'm looking at all the forces acting on the joint. There is a force pulling it up in this direction. We assume there is a force pulling it to the right, and there is a reaction pushing it up. So here, because I got a negative, it means that would be a compression. The arrow is going into the joint. It's pushing the joint. So it's negative. So we say 225 divided by sine 45. You get 200, negative 264.4 pound equals 264.4 pound compression. C stands for compression. Like we said with the reaction, you don't have to to erase it and draw the arrow going into the pin. No, we know it's negative. So you can leave it and use negative for that, or assume it's going down and use positive value. It's up to you. But now I'm going to say summation of the forces in the x direction equals 0. We said AB is going to the right, so it's positive. And if I use AD as it's drawn, I say plus AD cosine 45 degrees equals 0. Notice AD is negative 264.4. So when I move it to the other side, AB would be equal to AD cosine, or it should be negative AD, but if I can write it as 264, so let's write it negative AD cosine 45. Oops, AD is already uh, negative. So negative times negative is positive. I'm going to say this cosine, no, I'm sorry. This cosine 45, meaning half of what I started with, 138. No, that doesn't make sense. Do I have the mode? Yeah, the mode is radian. That's what I was worried about. I forgot to change that. Oops. So basically this is not correct. 225 divided by sine of 45 equals 318.2. It's negative 318.2 or 318.2 compression. So now I'm going to take that number, oops, this number and multiply it by cosine 45, and it should be positive, right? I get back to 25 tension. Okay, I found AB to be tension and AD to be compression. Now I can either go to D or to B. B is so easy, right? Why? Here is the free body diagram of joint B. Now at B, I have, notice, AD was tension, meaning going away from B. And I have BC, I'm going to assume it's tension also. And then there is BD that I told you it's a zero force member. Try to do some of the forces in the Y equals zero. There is only BD, so you say BD equals zero. So summation of the forces in the Y equals zero, BD equals zero. We already knew that. That's a zero force member. Summation of the force in the X equals zero. That's a very easy thing. BC going to the right minus 225 going to the left equals zero. So BC equals 225 pound, also tension. Of course, these are two members back to back, so they must be equal in magnitude and opposite in direction, meaning both of them are trying to pull joint B to its side. Of course, they have to be equal or else the truss would move, right? So we know that these two forces are equal and opposite. Opposite not meaning one tension, one compression. No, opposite. The arrows are both one going to the right, one going to the left, and both are trying to pull. So you are standing here, and two of your friends are trying to pull you towards them. If they pull with the same force, you are staying in place. You are B. Okay. I'm not making fun. I'm sorry if you got. Okay. After that, we can move to joint C. Notice, we already found this guy. We already found this guy. We already found that guy. We already found this guy. So we used, so to speak, six equations, right? Some of the force in the X and Y at A, some of the forces X and Y at B. And now I'm going to use two equations, some of the forces X and Y at C. We also use um, three equations of equilibrium outside, right? So, excuse me. And we will have, so we will have free body diagram of joint C. At point C, I have the reaction CY. Remember, it was 225 going down. CX is 450 to the right. BC, we already know it, right? BC, we already found it. It's 225 to the left. So I only have one unknown. So I use 2 here and 2 there, 4. And here I'm going to use this equation. So I have CD. Notice we said we have 8 equations of equilibrium, 2, 4, 6, 8. We used, again, we use 2 at A, 2 at B, that's 4. I still have 4 remaining. No, I don't. I use some of the forces in the moment, some of the forces in the X, some of the forces in the Y. So I only have one equation remaining. You can use it either some of the forces in the X or some of the forces in the Y. Why? Because I only have one unknown, and this angle is 45 degrees. You can say CD sine 45 minus 225 equals 0, and that's it. You don't need anything else. Or you use some of the forces in the X. In fact, it's much easier to say some of the forces in the Y equals 0. I have CD sine 45 minus 225 equals 0, which is exactly like that, right? But the only difference is that this is negative instead of positive. So I should get 318.2 tension. CD equals 225 over sine 45 equals, we already did it, it's just a repeat, 318.2 pound, and it's tension because it's going away. And we found all the forces. This was a zero force member. We found these 4 along with the 3 component of the reaction. I was intending to do a second problem, but I see that this session was long because we talked about the trusses, what they are made of, and so on and so forth. So probably, I don't know if we'll take one more or two more sessions, at least one session where I'm going to work out the other problem and then start discussing the method of sections. Or I will do the other problem, talk a little bit about zero force members, and then we'll have a third session just to be sure we complete everything on the method of sections. I hope this wasn't confusing. I know in the beginning it's a little, you know, complicated, but keep in mind that we don't see the force inside the members unless we cut one joint or we cut a whole section like we will be doing in the method of sections. But as long as the truss is intact, the only things you see are the external forces like the 450. And then when you take off the pin and the roller, you see the internal forces, the internal reactions. Again, there is an AY going, pushing the truss up, and there is an AY pushing the soil down, and they cancel each other. And it's not correct to draw them because you cannot draw one without the other. Only when you take away these supports you can see what they are doing to the truss. This AY is pushing the truss up. This CY is pulling the truss down. Remember? CY was negative, going down. And CX is pushing the truss to the right. Anyway, so I hope this wasn't bad enough. And you understood the method of joints. Again, I'm going to work another example next time with the method of joints. So to consolidate your knowledge. And if you have any questions, as usual, I ask you to write me a comment and leave it in the comment section, and I will get back to you as soon as I can. Thank you very much for watching and hope to see you soon. Have a nice day.